Hello students. Today our topic is mass defect and binding energy per nucleon. But before that I would like to talk a little about the isotopes, isobars and isotones. Isotopes of an element are the atoms of the element having same atomic number, that is Z value is same but different mass number A. H1, H2, H3 are the isotopes of hydrogen, which are known as hydrogen, deuterium, and tritium respectively. C12, C13, C14 are the isotopes of carbon, having mass numbers 12, 13, and 14, and they have same number of protons and same number of electrons. Cl35 and Cl37 are the isotopes of chlorine. The isotopes of an element have identical chemical properties, however, their physical properties differ. Isobars are the atoms of different elements having same mass number A but different atomic number, that is Z value. So isobars have different numbers of protons, different numbers of electrons, as well as different numbers of neutrons. But same number of nucleons, that is total number of protons and neutrons, are same. Sodium 22 and nitrogen 22 are isobars. Chlorine 37 and sulfur 37 are also isobars. Some more pairs are calcium 40 and argon 40, then carbon 14 and nitrogen 14, cesium 76 and selenium 76 are also isobars. Isobars have different atomic structures and therefore they have different chemical properties, but their physical properties may be identical. Isotones are the atoms having same number of neutrons, that is A minus Z value, but they have different mass number. Chlorine 37 and potassium 39 are isotones. For both, A minus Z is 20. Some other pairs of isotones are hydrogen 3 and helium 4. Oxygen 16 and carbon 14 are also isotones. Now we consider the mass defect. It has been observed that rest mass of a nucleus is always slightly less than the sum of the rest masses of its constituent particles, that is free neutrons and protons. This difference between the sum of the masses of free neutrons and protons with the rest mass of the nucleus is known as mass defect. This mass defect appears in the form of binding energy, which is responsible for holding the nucleons together in the nucleus. If nucleus having atomic number Z and mass number A has the rest mass m, then the mass defect delta m is equal to Z times mp plus A minus Z times mn minus m. The stability of atomic nucleus indicates that nucleons in nucleus are bound together with some strong short-range interacting forces called short-range nuclear forces. In order to separate the nucleons from the nucleus to such a distance that there is no interaction between them, a definite amount of work has to be done, which is the measure of binding energy of the nucleus. So we can say that the binding energy of a nucleus is the energy with which nucleons are bound together in the nucleus. It can also be defined as the energy required to separate the nucleons an infinite distance apart from one another so that they may not interact with each other. The binding energy is related to the mass defect by Einstein's mass energy equivalence. Binding energy EB is equal to delta m into c square, where, as you know, c is the velocity of light in vacuum and delta m is the mass defect. Therefore, EB is equal to z times mp plus a minus z times mn minus m whole into c square. The binding energy is the indicator of stability of the nucleus. It is the measure of strong bond between the nucleons which holds them together. The more useful measure of this strong bond is the binding energy per nucleon, which is the average energy required to remove a nucleon from the nucleus to infinite distance. It is the total binding energy divided by the mass number A of the nucleus. So, binding energy EBN is equal to EB by A. The variation of binding energy per nucleon with mass number is shown in the plot. The information that binding energy curve provides are average binding energy per nucleon for light nuclei like hydrogen and its isotopes is very small. For mass number ranging from 2 to 20, there are sharp peaks in the curve that correspond to helium 4, carbon 12, oxygen 16. These peaks indicate that these nuclei are relatively more stable than other nuclei in their neighborhood. In the range from 30 to 120, the binding energy curve corresponds to average binding energy per nucleon, which is equal to 8.5 mega electron volt. The maximum or peak value of the curve corresponds to mass number 56, that is iron 56, for which the value of binding energy per nucleon is 8.8 mega electron volt. Iron has the most stable nucleus. For the mass number beyond 120, the value of binding energy per nucleon decreases and falls to 7.6 mega electron volt for uranium 238. This decrease may be due to Columbian repulsion between the protons. Therefore, the heavy nuclei are relatively less stable. Binding energy per nucleon is low for both light nuclei, for which mass number A is less than 30, and heavy nuclei, for which A is greater than 120. With this, we get important conclusions. The decrease in binding energy per nucleon at higher mass numbers indicates that nucleons are more strongly bound when they are assembled into two middle mass nuclei than in a single high mass nucleus. It indicates that energy can be released in the nuclear fission of a single massive nucleus into smaller fragments. The smaller values of binding energy per nucleon at lower mass numbers indicate that energy can be released if two nuclei of smaller mass numbers combine to form a single middle mass nucleus, which is fusion, the reverse process of nuclear fission. We find that the middle mass nuclei are more stable. Let us now review the nuclear force. In the nucleus, a number of protons along with neutrons are held in such a tiny volume, so there must be a very strong force of attraction between them. This force of attraction is called short-range nuclear force. And this force is much stronger than the Columbian force of repulsion between the protons in the nucleus. In fact, the short-range nuclear force is 100 times stronger than the electrostatic force of repulsion between the two protons in the nucleus. This force acts within the nuclear range, which is about few femtometer or Fermi. The nuclear force between two protons or two neutrons or a proton and a neutron is approximately same, irrespective of their charges. This means the short-range nuclear force is independent of charge. The given plot of variation of potential energy EP with separation R of the two nucleons indicate that potential energy is minimum at a distance R0, which is about 0.8 femtometer. It means the force is attractive for separation larger than R0 and it is repulsive for separation less than 0.8 femtometer. Okay, this much for today. Next time our topic will be radioactivity. See you in the next class.